Good morning, everyone. So welcome to my YouTube channel, Math Program. So today we are going to see another lecture number 23 on Riemann integration. Today we will study generalized first mean value theorem for Riemann integration. Okay. So let's start today's topic now. So what is generalized first mean value generalized first mean value theorem for Riemann integration. So what is this theorem? Let F and G belongs to RAB. It means F and G are Riemann integrable. Okay. And either Gx is greater than equal to for all X belongs to closed interval AB, or Gx is less than equal to for all X belongs to closed interval AB. Okay. Then there exists lambda belongs to R with lambda lies between bounds of capital lambda lies in between the bounds of small f function where m is infimum of f and capital M is supremum of f on closed interval. Okay. Such that there exists lambda belongs to R such that lambda lies in between the bounds of f function such that the integral a to b f g x dx, okay, dx is equal to lambda times a to b gx dx. Or it means you can write this in a you can open this the meaning of fg. You can write like that: fgx is equal to fx into gx. Okay. A to b fx gx dx is equal to lambda times a to A to B GX TX. Okay. So we'll prove it. How it follows. So we will prove this theorem for GX greater than equal to 0 for all X belongs to AB. Okay. The case GX less than equal to 0 for all X belongs to closed interval AB can be proved similarly. Okay. Can be treated similarly. Okay. So we are proving the theorem for, we are assuming that our GX is greater than equal to 0. The case GX less than equal to 0 can be treated in similar manner. Okay. Okay. So we have what we have. We have M, small m is less than equal to Fx less than equal to capital M for all X belongs to closed interval AB. Okay. So multiplying both the sides by GX. Okay. GX. Okay. Because GX is greater than equal to 0, so this equality will remain as it is. It will not change. Okay. Because GX is non-negative, inequality will not change. Okay. That is why GX is taken either greater than equal to 0 or less than equal to 0 for all X belongs to AB. Okay. Since GX is greater than equal to 0. Okay. Now, we have what we have. We can take integration. So M is constant. It will come out A to B GX dx A to B Fx GX dx less than equal to capital M A to B GX dx. Okay. Okay. Now, let's say equation number 1. Since GX is greater than equal to 0 for all X belongs to AB, for all X belongs to AB, we get the integral A to B GX dx is greater than equal to 0. Okay. Okay. So therefore, either A to B GX dx is greater equal to 0. This is 0, or A to B GX dx is strictly greater than. Now, if A to B GX Okay, dx is 0. Okay, okay. Then from 1, then from 1, we have, this is 0. What is from equation? This is a to b gx dx less than equal to a to b fx gx dx. Now this part is 0. This part is 0, so I can put here 0 a to b fx dx dx. Okay. Okay. So what does it mean? Now this part is also 0. So this part is 0 a to b fx gx dx less than 2. So this implies a to b fx gx dx is equal to 0. Okay. So in this case, so we can choose, we can take any lambda is equal to x naught for some x naught belongs to AB. Okay. Then obviously lambda is equal to fx naught is in between which. Okay. Such that A to B, this is, we have proved that this is 0. This is 0. But A to B, gx is also, this part is also 0. We know that this part is 0 because we are taking the case where it is 0. Okay. So I can multiply with lambda. It will become 0. Okay. Because A to B gx integral is 0. Okay. So both the quantities are 0. You multiply with any lambda, so it will be 0. So this implies A to B fx gx is lambda times A to B gx dx. Okay. So in this case, theorem is proved. Okay. If A to B gx integral is 0. Okay. So you can say this, case number first here. You can say case first here. Case first. What is case first? If this integral is 0, in that case we have shown that the theorem follows. Okay. In that case, you can take any lambda, where lambda is obtained from functional value x naught belongs to AB. Okay, that will work. Okay. Now if case second, if lambda, if A to B gx dx integral is greater than 0, then from equation 1 we have what we have m times A to B gx dx is less than A to B fx gx dx less than equal to capital M A to B gx dx. Okay, so dividing both the sides by A to B gx dx. Okay, we get what we get, because we are dividing, because A to B gx is greater than 0. So because we are dividing by the positive quantity, so this inequality will not change. Okay, so what we get? We get M less than, okay, A to B fx gx dx is upon A to B gx dx, and that is less than equal to capital M. Okay, so put lambda is equal to A to B fx gx dx upon A to B gx dx. Okay, then we can put this value here. Then lambda lies in between this, such that lambda is equal to, okay, so lambda lies in between this, and we can solve it now. We can solve it. This equation we can solve it. Then what we will get? We get A to B fx gx dx is equal to lambda times A to B gx dx. Hence, this theorem is true. Hence, the theorem is true. Okay. In both the cases, we have proved the theorem. Okay. So, this theorem has been the when gx is greater than equal to 0 for all x belongs to AB. The case gx is less than equal to 0 can be treated in a similar manner, and theorem can be proved. Okay. So, theorem is done now. Okay. Now we are going to see a corollary. Now, if let f closed interval AB to R be continuous and G is Riemann integrable over closed interval AB. Okay. Then there exists, okay, x naught belongs to closed interval AB such that A to B, sorry, one minute. I have not written. And gx is a function, Riemann integrable function. such that gx is greater than equal to 0 for all x belongs to closed interval AB. Such that either gx is greater than equal to 0 for all x belongs to AB, or gx is less than equal to 0 for all x belongs to AB. Okay. Then there exists x naught belongs to closed interval AB such that A to B fx gx dx is equal to fx naught into A to B gx dx. Okay. So this is simple. Okay. We know that if f is continuous, f closed interval AB to R is continuous. Okay. Okay. So this implies f belongs to R AB. Okay. Now we have f G belongs to R A B. Okay. Because every continuous function is Riemann integrable, so f belongs to R A B. Now we have f or G, f and G are Riemann integrable, and either gx is greater than equal to 0 for all x belongs to closed interval AB, or gx is less than equal to 0 for all x belongs to AB. Now by generalized mean value theorem, by generalized first mean value theorem. Okay. Theorem. We have A to B fx gx dx is equal to lambda A to B dx dx for some lambda in between this, where m is infimum of f, and capital M is supremum of f on closed interval AB. Okay. Okay. But f is continuous on closed interval AB by intermediate by intermediate value theorem. Intermediate value theorem. There exists X naught belongs to closed interval AB such that lambda is equal to f x naught. Okay. So what is the intermediate value theorem? You take, because supremum and infimum is always attained by a continuous function. So a small m will be some f(x1) and capital M will be some f(x2). Image m will be attained, capital M will be attained, and small m will also attained. So they will be, small m will be is sum equal to f(x1), okay, and capital M is equal to f(x2). Okay, so you are taking value lambda in between the functional value of continuous function. So that will be also attained by intermediate value theorem, because okay. So lambda, that is why lambda is equal to f(x0) for some x0 belongs to closed interval. Okay. Okay. So therefore, hence there exists x0 belongs to closed interval AB such that A to B fx gx dx is equal to f(x0) A to B gx. So this is proof. Okay. Okay. Now remark, if f belongs to R A B, then there exists lambda belongs to R such that m, small m, is less than equal to lambda less than equal to capital M. Okay. Such that, so I am writing here with, okay. Such that A to B fx dx is equal to lambda times B minus A. Okay. So this was the first mean value theorem. Okay. This is first mean value theorem. Okay. This is first mean value theorem. We have already first mean value theorem. Okay. For Riemann integration. That was the first mean value theorem for Riemann integration. So it follows from the remark. Why? You see its proof. In theorem, in today's theorem, in generalized first mean value theorem, take gx is equal to 1, that is greater than equal to 0, for all x belongs to closed interval AB, we get what we get A to B fx dx, that is equal to A to B fx. Now gx is 1 here, so 1, so that is lambda A to B by generalized mean value theorem, first mean value theorem. So what is this now? Lambda B minus A. Okay. So this is equal to A to B fx dx is equal to lambda D minus A. Okay. This is first mean value theorem for Riemann integration. Okay. Now remark 2. If f closed interval AB to R be a f AB to R is a continuous function. Is a continuous function. Then there exists x naught belongs to closed interval AB such that A to B fx dx is equal to fx naught into B minus A. So this is first mean value theorem for continuous function. We have done it. Okay. So let's see its proof also. F closed interval AB to R is continuous. Okay. It's continuous. Take gx is equal to 1, that is greater than equal to 0 for all f belongs to closed interval AB. By corollary, there exists x naught belongs to closed interval AB such that A to B fx gx dx is equal to fx naught A to B gx dx. But gx is 1. So gx function is 1. Okay. So gx is 1. Okay. So we put the value of gx because gx function we have taken 1. Okay. So put the value gx here. A to B 1 dx. So what is this? So this is integral. This is integral A to B fx dx is equal to fx naught A to B GX dx. Sorry, this is, and what will be this integral? Integral, we are taking integral this will be b minus a. Okay, integral a to b 1 dx. Okay, this integral will be 1. Okay. The integral will be b minus a. Okay, so which is, so this is from which is first mean value theorem, value theorem for continuous function. Okay, so this is done. So today's lecture up to this, in this lecture we have studied what is generalized mean value theorem. Okay, we also proved generalized mean value theorem for continuous function, that is corollary, and we achieved this. We achieved the first mean value theorem for Riemann integration, and first mean value theorem for continuous function for this generalized mean value theorem for Riemann integration, Riemann integrable function, and for continuous function. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. We will see you in next lecture. Thank you very much.